Welcome to Lecture 3.8, Pythagoras, Parseval, and Plancherel. Let's take a few moments to summarize our journey from Rn, in the first few lectures, to Fourier transforms, where we are now. In the beginning of this class, we started with standard Euclidean space, Rn. The dot product gave us a notion of geometry. We got lengths, angles, and projections. Our favorite orthonormal basis was the standard unit basis vectors E1 up to En, though any orthonormal basis is really just as good. Moving on to the space of piecewise 2L periodic functions, that's an infinite dimensional vector space, we defined an inner product, that's a generalization of the standard dot product for general vector spaces, and this gave us a notion of geometry. We were able to define norms, angles, and projections in this vector space just like we did in Rn, and other things as well. We didn't use angles that much, but we certainly used orthogonality, which really is like a right angle. Our favorite orthonormal basis was the infinite set of complex exponentials e to the I pi nx over L, where n ranges over the integers. Well, I say our favorite, it's really my favorite. Maybe you prefer the sines and cosines. Finally, let's let L2 of R be the set of square integrable functions. So first of all, when I say L2 of R, I mean the domain is R. So a function f is going to go from R to either R or C. So it's okay if it's complex valued. We just want the inputs to be R. Because then when we say square integrable, we mean that if we integrate f of x squared over the entire real line, then that integral converges. It's something finite. Now, why do we care about that? Well, if we define the inner product of f and g to be the integral over the real line of f of x, g of x, dx, well, if these are complex valued, I need to put a bar here, then the norm of f squared is defined as the inner product of f with itself, which is the integral of f of x, the absolute value of f of x squared dx. So if this integral doesn't exist, then the function doesn't have a norm. It doesn't really make sense to speak of the vector space of these vectors if some of them are infinite dimensional. So for example, it's sort of like if we were to look at the space of continuous functions, and then I write 1 plus x squared plus x cubed plus etc. Well, this is a perfectly good power series. If we try to compute its norm based on how we define the norm of continuous functions, it's not going to be finite. Similarly, if we look at the vector e1 plus e2 plus e3 plus etc. in maybe R infinity, well, this is a perfectly good expression. If we try to compute the norm of this by the Pythagorean theorem, it's not going to be finite. So basically, we really only want to deal with functions that are vectors in the sense that they actually have a finite norm, and that's why we require them to be square integrable as well. The Fourier transform of one of these functions can be thought of as a continuous version of a Fourier series, and we saw this in the last lecture. Now, there were several ways to define the Fourier transform of a function f and its inverse. So we defined it as f hat of omega is the integral over the whole real line of f of x times e to the I omega x dx. And the inverse transform is the same thing, but we have to stick this 1 over 2 pi out in front. And then this negative exponent becomes positive. And that's just there because it has to be there if we want this to be the inverse transform. So the way to think about this is you have a function f of t or of x, either one, and you apply this Fourier transform and you get a function f hat of omega of angular frequency, and then the inverse transform, f inverse, just brings you right back. So think of omega as angular frequency. Another definition of the Fourier transform that we saw was in terms of oscillatory frequency, c, which is omega over 2 pi. Because if you go around a circle once, then you've traversed 2 pi radians, but only one cycle. So that's a factor of 2 pi. And this definition, called it f tilde. Now every book is going to have it as f hat, but I'm using different superscripts or markings just because I want to distinguish them. So I called it f tilde of c as the integral over the real line of f of x e to the minus 2 pi I c x dx. So basically it's the same as the angular frequency one, just in terms of, or instead of omega, we stick in 2 pi c right there. And that's the only difference. Then the inverse transform, we don't actually need this 1 over 2 pi out in front. So it's really the same thing, except instead of a positive exponent here, we have a negative exponent. Now, you may wonder why this is so popular, because this is actually probably the most popular definition of the Fourier transform, because as I presented it last lecture, it was the limit of a Fourier series of a finite signal if we made it periodic and then sent that period to go to infinity. And this exponent, e to the I omega x, looks more natural as a limit of Fourier series than having a 2 in there. However, there are a lot of people who express Fourier series differently. There's more than one convention for that as well. So for example, some people write a Fourier series where Cn is the integral of 1 over L from negative L to L. So they look, L over 2 to L over 2. So they're looking at L periodic functions, not 2L periodic functions. And then I think it's C of x e to the negative 2 pi I n x over L. So you have an extra 2 in there. I should put a dx here. So basically, your function is only half, or your interval is only half the width, and these are your orthonormal bases. So, but the integral has to be a little bit different. The inner product is different. So if you think about it, you're really doing the same thing. It's just you happen to have a 2 in here, and so you have more 2's in here. And some people would say that, well, this is a more cumbersome definition of the Fourier series because you got more 2's. However, the Fourier transform ends up working out nicer, and that's why a lot of people prefer this definition of the Fourier series. So that's not the one that we're using, but they really are equivalent, except for when you get formulas and relations that sometimes you have an extra 2 pi out in front. At this point, I want to take you on a journey back to a celebrated theorem of the ancient Greeks. I was intending to leave this as a surprise for you, so you didn't know what was coming, but then I came up with the title of the 3 mathematicians, starting with a P, and I just couldn't resist. So you probably know where this is going, and of course that is the Pythagorean theorem for vectors in Rn. Given a vector v equals c1, e1, all the way up to cn, en, the norm squared of the vector is the inner product, or the dot product, of v with itself, which is just the sum of the squares of the CIs. Now, you're probably mostly used to this in R2, or actually just for plain old triangles, but it's easy to see why that's equivalent. So if you have a right triangle of base A and height B, then let's call one side the origin, 0, 0, and the other side the vector AB, and let's call that V. And now the norm of V is the square root of V dot V, and that's just the square root of A squared plus B squared. So this, of course, holds not just in 2 dimensions, but in n dimensions. And actually, it holds more generally. Parseval's identity for Fourier series in the space of 2L periodic functions can be thought of as a generalization of the Pythagorean theorem. So I'm going to give this to you piece by piece and see if you can guess what the next step is at each time. If you need to pause the lecture, do it. Okay, so we start out with a Fourier series, a complex Fourier series, so we're summing over all integers n, Cn e to the I pi nx over L. Now, this function has a norm, and so the norm squared of that function is just the inner product of f with itself. And we have a definition of that in terms of an integral, which is 1 over 2L times the integral from negative L to L of f of x norm squared dx. Now, you think of what's coming next? If you guessed that's equal to the sum of squares, then you were right. This is equal to the infinite sum of the CNs. So it really is a generalization of what we know and love in Rn. I'm not going to prove this version, but a couple slides later, I will prove an analogous version for Parseval's identity for the real Fourier series. So it's going to be in terms of the ANs and the BNs. And the proof is going to be pretty much the same. I think I actually might leave it as a homework exercise for you. Finally, the last generalization of the Pythagorean theorem is Plancherel's theorem for Fourier transforms in L2 of R. And this is actually a special case of a more general theorem of Parseval's identity, or maybe not more general, but a continuum version. So there's a version of Parseval's identity for Fourier transforms as well, and a special case of that is called Plancherel's theorem. It's poor naming. Really, Plancherel's theorem should be the big theorem, and this one should be Parseval's identity for Fourier series. But oh well, what are you going to do? So if f is square integrable, now I probably should also say that f is absolutely integrable. So that just means that the absolute value of f is finite. But there are technical reasons why sometimes you can drop this condition. I'm not going to get into it. It's beyond the scope of this class. So if you're worried about that, I encourage you to look into it. But most of you, just assume that f is square integrable. It's in L2 of R. Then the norm of the Fourier transform of f squared, which by definition is the inner product of f hat with f hat. We also have a definition of that in terms of an integral. That's just the integral over the real line of f hat of c squared dt. And when I say squared, I mean norm squared, because it could be complex valued. And here's the theorem, this equality, that the integral of the absolute value of the Fourier transform of f squared is equal to the integral of the plain old function f of x, quantity squared, absolute value dx. And that is, of course, the inner product of f with itself, which is just the norm of f squared. So the real takeaway message here is this equality, that the norm of f equals the norm of the Fourier transform. So in other words, if you start with a function f of x, or f of t, and you apply the Fourier transform, and you get a function f hat of omega, then that's distance preserving. That preserves the norm. And I should say that this does not necessarily work if you use some of the other definitions of the Fourier transform. If you use the opposite definition, where there's a 1 over 2 pi in here, you're going to get out a factor of 1 over 2 pi here. But if you use the definition, the canonical definition, let me write this, so I'm going to put a hat there. If you use the definition in terms of oscillatory frequency, f of c, f hat, or f tilde of c, then this is going to work as well. So again, the takeaway message here is that this linear transformation, or this linear operator called the Fourier transform, preserves distances. And actually, it preserves more than that. So we'll see in the next slide that there's a generalization, or not really a generalization, there's a result called Parseval's identity for Fourier transforms, which says that not only does this preserve distances, but it preserves angles. And I personally think that the name of that result and this result should be switched, but maybe that's just me. Plancherel's theorem says that the Fourier transform is an isometry. It's a rigid motion. It preserves distance. This follows from a more general result. This is called Parseval's identity for Fourier transforms. It says if you have two functions that are in L2 of R, again, they probably should also be in L1 of R, they should be absolutely integrable, then their inner product, f dot g, is equal to the inner product of the Fourier transforms, f hat dot g hat. So this is saying that not only does the Fourier transform preserve distances, but it also preserves angles. And I should say that once we prove this, then Parseval's theorem falls out right away. You see how and why? Well, just set g to be equal to f, and you get right away Parseval's theorem, which is a special case. Okay, so let's prove this. Let's begin by defining h of x. This is going to be a function which is just f of x times g of x bar. And what I'm going to do is I'm going to compute I'm going to compute the Fourier transform of this and plug in 0. So first of all, the Fourier transform of h is by definition the integral from negative infinity to infinity of f of x g of x bar times e to the minus I omega x dx. Okay, so why did I do this? Well, if I plug in 0 into here, then this becomes a 1, and I just get the inner product of f and g. You see that? So note that h hat of 0 is the integral from negative infinity to infinity of f of x g of x bar times 1, which is dx, which is just the definition of f dot g. Okay, so now I'm going to compute this a second way. So that's one thing to note. And then next, I'm going to write also h hat of 0. Another way to do this is to use the convolution of f and g. And I know we haven't done that much in this class, but hopefully you've seen this in Laplace transforms, and I did mention it in the previous lecture. So this is so the Laplace transform, the Fourier transform of this is a product is the convolution. So it's f hat star g bar hat evaluated at 0, because we're plugging in 0 to both sides. So this is, by definition, the integral from negative infinity to infinity of f hat of tau g bar hat of usually t minus tau, but since we're plugging in 0 for t, I'm going to write 0 minus t d tau. And then I'm going to write as a lemma, I will encourage you to check this, that g bar hat of negative tau is equal to g of tau bar. So check that. It's just using the definition. And here's a hint for that. E to the I omega x equals cosine of omega x plus I sine of omega x. And now think about even and oddness and this identity. Okay, so this integral is f hat of tau times g of tau bar d tau, and this is exactly what the inner product of f hat and g hat is. Oops. And that's exactly what we wanted to show, is that these two things are equal, and we did that by showing that both of them are equal to the Fourier transform of the product of these evaluated at 0. We did that two ways, once using the definition and the other using the convolution theorem. So that's the end of the proof. Let's put a box here and move on to the next slide. And recall that this implies Parseval's theorem from the previous slide. Just take g to be equal to f. As I mentioned earlier in the lecture, and it shouldn't be a surprise, that there is a version of Parseval's identity for real Fourier series. So if f of x is written in a real Fourier series, so let's say a naught over 2 plus the infinite sum of an cosine of n pi x over L plus bn sine of n pi x over L. Then the norm squared of f, which, as before, is the inner product of f with itself. But now the definition is slightly different because the inner product is a little bit different. It's 1 over L times the integral from negative L to L of f of x quantity squared dx. So what do you think comes next? Did you get it right? Or did you miss this pesky 2 sitting right here? Now that's all because of the fact that the norm of the constant function 1 equals root 2. And so you need to scale, you need to normalize it, divide by root 2 to get something of norm 1. And that's all has to do with why we have an a naught over 2 here instead of just a plain old a naught. Okay, so this is the analog of Parseval's identity for a real Fourier series. And let's prove it. So how are we going to prove this? Well, what we have to prove is this equality. That's the theorem part. These parts are just definitions. So let's write out what we have. We have 1 over L times the integral from negative L to L of f of x times f of x. Now, instead of my putting a squared here, I'm going to just stick another copy of f of x right here. And here is a copy of f of x. I'm going to write the Fourier series right there. So that's a naught over 2 plus the sum of an cosine of n pi x over L plus bn sine of n pi x over L dx. Now let's break this into 3 sums. So this first sum is just a naught over 2. I can pull that out. And then I have this thing here. So let's write that as a naught over 2 times 1 over L times integral of, from negative L to L of f of x dx. Now, this thing here, before I go any further, that should remind you, this integral, of something. What is it? That's the definition of a naught. So far, so good. This first term is a naught squared over 2, and that's exactly what we needed right here. Okay, so what do we have next? So now, I'm going to write this as plus 1 over L times, I'm not going to do much difference here. I'm just going to write the integral of f of x times infinite sum from 1 to infinity of an cosine of n pi x over L plus bn sine of n pi x over L. And then let's put a dx here. So this is the integral of this infinite sum. So let's move the integral inside and write this as the sum of infinite sum of a bunch of integrals. Now we can't always do that with integrals and sums. That's a technical thing that if you take usually a second year undergraduate analysis course, or maybe a first year graduate analysis course, you'll learn when you can do that and when you can't. So this is where I'm going to wave my hands a little bit and say that here you can. So let's go on and say this. Well, I've already said that this is a naught squared over 2. So a naught squared over 2. But now I'm going to write this as, I'm going to write this as the infinite sum from n equals 1 to infinity of, what else can I do? I can also pull out, let's see, can I pull out? I have to be careful here. I can't pull out this and just, well, let's see, how do I want to do this? Yeah, I'm going to write this as an times 1 over L times the integral from negative L to L of f of x cosine of n pi x over L. So again, I move the integral inside. So I move this thing right here, and then I move I move this whole thing inside because the f of x, I can do that. So basically what we did is we took this piece and we moved it right there. Oh, actually, I should say right there, and also right there. And then we have a second term. So this is the big sum here. And the next term is going to be, I put my dx, and then plus bn times 1 over L times the integral from negative L to L of f of x sine of n pi x over L dx. Okay, now these things, these integrals, should remind you of something. What do they remind you of? This first one is the definition of an. And this second one is the definition of bn. And that's exactly what we want. We have an squared and bn squared. So now we can write this as a naught squared over 2 plus the infinite sum of n equals 1 to infinity of an squared plus bn squared. And that is the end of the proof, assuming that you believe me that I can swap the order, that the integral of the sum is just the sum of the integrals. Now again, that always works when things are finite. The only detail is if it's infinite, you may have some problems, and generally you do, but in this case, it works, and that's the crux behind Parseval's identity for the real Fourier series. I'm going to conclude this lecture and this section on Fourier series and transforms with a fun application of Parseval's identity. We're going to use it to compute the sum of the inverse squares. This is the sum from n equals 1 to infinity of 1 over n squared. So just 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25, and so on. It's not clear what this sum is going to converge to. And I think this is really cool because this is a problem from number theory, basically, or combinatorics. That's probably a better way to describe it. And we're going to use this technique that comes up in engineering and physics and was invented to solve solutions to the heat and wave equation and partial differential equations. So we're going to use that applied technique to solve this fun little combinatorics problem. And in fact, I don't know any other way to do this. There probably is another way. This is just the only way that I know. It's definitely the easiest way to sum this series. So I'm going to give you a function that you probably don't expect. So let f of x equals, you didn't expect it to be easy, right? It's not like Parseval's identity is going to be shouting this out to you. But if you define f of x to be x on negative pi to pi, and you extend this to be 2 pi periodic, well, let me sketch this function. Now we have seen this Fourier series before. We've computed it, so I'm not going to recompute it. I'll tell you what it is. So this function, obviously an's are 0 because f of x is odd. And then bn is 2 over pi, integral from 0 to pi. We don't need to do that. We can go from negative pi to pi if we want. But I'm used to, because it's n, because it's odd, that is, to just do this, of the function x times sine of nx dx. And if you do this, you may recall that we get 2 over n times negative 1 to the n. Okay, and I'm just going to say right now that means that the bn squared, that's something that comes up in Parseval, is equal to 4 over n squared. So now let's recall what Parseval says. So Parseval's identity says that the norm of f squared, which is just the inner product of f with itself, that is, well, that's 1 over pi times the integral, well, from negative pi to pi, the integral of negative pi to pi of x squared dx. Let's just quickly compute that. That's x cubed over 3 pi from negative pi to pi. And so that's pi cubed minus negative pi cubed over 3 pi. Make that plus plus. And we have 2 pi squared over 3. So, okay. And Parseval's identity says that this is equal to a naught squared over 2 plus the infinite sum from 1 to infinity of an squared plus bn squared. And what is that? Well, the an's are equal to 0, and the bn's are equal to 4 over n squared, or the bn squareds are. So we have the sum from n equals 1 to infinity of 4 over n squared. Now this is almost what we want. Look, what we want is 1 over n squared. So all we need to do is set this equal to 2 pi squared over 3, and we're done. So let's take 4 times the infinite sum from n equals 1 to infinity of 1 over n squared, and that equals 2 pi squared over 3. So if we divide both sides by 4, we get that the infinite sum that we are seeking, 1 over n squared, equals, what is that? 2 pi squared over 12, which is pi squared over 6. So I bet you didn't see that one coming, that this infinite square, or that this infinite sum of the squares, the inverse squares, is pi squared over 6. Okay, so that's a fun application. And on your homework, I think I'm going to have you do the same thing, but with the sum of the fourth powers, or reciprocal of the fourth powers of n, and you'll get something you probably didn't expect either. So with that, I think I will leave it there. And in the next section, we will study boundary value problems and Sturm-Liouville theory. It's a lot of fun, so stay with us.